In this module, we shall learn about partial and multiple correlation. We will first understand the meaning of correlation. The correlation is a statistical tool which studies the relationship between the two variables, and correlation analysis involves various methods and techniques for studying the measuring the extent of relationship between the two variables. Two variables are said to be correlated if the change in one variable results in a corresponding change in the other variable. If the values of the two variables deviate in the same direction, that is, if the increase in the values of one variable results on an average in a corresponding increase in the values of the other variables, or if a decrease in the values of one variable results on an average in a corresponding decrease in the values of other variables, the correlation is said to be positive or direct. On the other hand, correlation is said to be negative or inverse of the variables deviate in the opposite direction, that is, if the increase or decrease in the values of one variable results on the average in a corresponding decrease or increase in the values of the other variable. Simple correlation measures the strength of the linear relationship between two variables, without taking into consideration the fact that both these variables may be influenced by a third variable. To analyze the relationship between two variables accurately, we need to eliminate the influence of other variables. Generally, a large number of factors simultaneously influence all social and natural phenomena. For example, when we study the correlation between price, dependent variable, and demand, independent variable, we completely ignored the effect of other factors like that of money supply, imports and exports, etc., which definitely have an impact on the price. Hence, partial correlation studies the linear relationship between two variables after excluding the effect of one or more independent factors. Consider a multivariate distribution with n variables, say x1, x2 up to xn. The study of the relationship between the dependent variable, say xi, and one of the independent variables, say xj, j not equal to 1, 2 up to n. After eliminating the linear effect of other independent variables on each of the variables xi and xj, or by keeping all other independent variables constant, is called the study of partial correlation. On the other hand, the study of relationship between the dependent variable, say x1, and the joint effect of all the independent variables x2, x3 up to xn on x1 is termed as the study of multiple correlation. After studying this module, you shall be able to, number 1, understand the concept of partial correlation, number 2, compute partial correlation, and number 3, comprehend the concept of multiple correlation. Compute multiple correlation, differentiate between partial and multiple correlation, identify the limitations of partial and multiple correlation. Let us begin by understanding partial correlation. Partial correlation explains the relationship between two variables while controlling for a third variable. The motive is to find out a unique variance between the two given variables and simultaneously eliminating the variance from the third variable. We define partial correlation coefficient as the correlation coefficient that exists between two variables x1 and x2, studied partially after eliminating the influence of the third variable x3 from both of them. We undertake partial correlation when the third variable has shown a relationship to one or both of primary variables. In other words, We first conduct correlation analysis on all variables so that we can check whether there are significant relationships amongst the variables, including any third variable that may have a significant relationship to the variables under investigation. Suppose we have three variables y, x2 and x3, then we define R12.3 equal to partial correlation coefficient between y and x2 holding x3 constant. R13.2 equal to partial correlation coefficient between y and x3 holding x2 constant, and R23.1 equal to partial correlation coefficient between x2 x3 holding y constant. The partial correlation coefficient given by R12.3, R13.2 and R23.1 are called first order correlation coefficients. By order, we mean the number of secondary subscripts. Zero order coefficient is a term defined to explain the simple correlation between two variables. It is called zero order coefficient since in simple correlation no factor is held constant. Thus, R12, R13 and so on are called zero order coefficients. A first order coefficient is a term used to define the partial correlation between two variables by keeping the third variable constant. It is called first order coefficient as in this case one variable is kept constant. In the same way, we can define a second order coefficient and so on as the third variable can be more than 1. The partial correlation coefficient varies between -1 and +1. Its calculation is based on the simple correlation coefficient. The partial correlation analysis has a great importance while studying the phenomena which have multiple factors influencing them, especially in physical and experimental sciences. In such cases, it is possible to control the variables and the effect of each variable can be studied separately. This technique is of great use in various experimental designs which various interrelated phenomena are to be studied. A more useful measure for interpreting the value of partial correlation coefficient is the coefficient of partial determination given by coefficient of partial determination is equal to square of partial correlation coefficient. Thus, if R13.2 is the partial correlation coefficient between x1 and x3, keeping x2 as a third variable, and R square 13.2 is interpreted as the proportion of the variation in y not explained by the variable x3 that has been explained by the inclusion of x2 into the model. If R13.2 is equal to 0.6, then the coefficient of partial determination is equal to R square 13.2, which is equal to 0.6 whole square is equal to 0.36. This implies that 36% of the variation in the variable x1 is explained by the plane of regression of x1 on x2 and x3 when the value of x3 is held constant. Let us look at the calculation of partial correlation. Partial correlation allows us to examine the relationship between two variables with the effect of the third removed from both. It statistically removes the systematic relationship by eliminating the linear trend, then correlate the residuals. Partial correlation coefficient is represented as Ry x1 x2, where y and x1 are two variables and third variable is x2. The partial correlation formula is as follows. R of yx1.x2 is equal to R yx1 minus R yx2 R x1 x2 upon square root of 1 minus r square yx2 into square root of 1 minus r square x1 x2. Through this formula, we are able to eliminate the impact of x2 on y and x1. We can also calculate semi-partial correlations. In this, we examine the relationship between two variables with the effect of the third removed from one. This formula is Ry of x1 dot x2 is equal to R yx1 minus R yx2 multiplied by R x1 x2 whole upon square root of 1 minus R square x1 x2. In this formula, we have removed the impact of x2 only on x1. Therefore, it is referred to as the semi-partial correlation. We can illustrate partial correlation with the help of an example. Illustration 1. We have to find correlation between the income and number of TV hours watched daily and eliminate the impact of number of years of education. Dependent variable is equal to income measured in dollars. Independent variable is equal to TV hours measured in daily hours watched. Control variable CV is equal to education measured in years. Hypothesis is given as null. There is no relationship between the number of TV hours watched daily and income, adjusting for the number of years of education, are equal to 0. Research. There exists a relationship between the number of TV hours watched daily and income, adjusting for the number of years of education. R is not equal to 0. If we control for the effect that education has on the relationship between number of TV hours watched daily and income, we find the following by doing a partial correlation with the data. We get partial correlation coefficient as R is equal to minus 0.11 and value of P is equal to 0.000. Suppose P is less than alpha, reject null. Hence, we can conclude that there is a weak negative relationship between the number of TV hours watched daily and income when we control for the effect of education. As the number of daily TV viewing hours goes up, income goes down for people of any level of education. R is equal to minus 0.11 and P is equal to 0.00. In other words, as income levels go up, the number of daily TV viewing hours goes down. R square is equal to 0.11 multiplied by 0.11, which is equal to 0.0121. Thus, when we control for the effect of education, the number of TV hours watched daily explains 1% of the variation in income. Or, when controlling for the effect of education, income explains 1% of the variation in the number of TV hours watched daily. Moving on to multiple correlation. The coefficient of multiple correlation is used to evaluate how well a given variable can be predicted using a linear function of a set of other variables. It is calculated by taking the square root of the coefficient of determination, but considering particular assumptions that an intercept is included and that the best possible linear predictors are used. Here, we study the effects of all the independent variables simultaneously on a dependent variable. For example, the correlation coefficient between the yield of paddy x1 and other variables, namely type of seedlings x2, manure x3, rainfall x4, humidity x5 is the multiple correlation coefficient R dot 2345. The coefficient of multiple correlation denoted by R, is a scalar which is defined as the Pearson's correlation coefficient between the predicted and the actual values of the dependent variable in a linear regression model that includes an intercept as well. In other words, in a trivariate distribution with three variables x1, x2, x3, Carl Pearson's correlation coefficient between x1 and the joint effect of x2 and x3 on x1 is the multiple correlation coefficient of x1 on x2 and x3 and is denoted by R1.23. In multiple correlation coefficient, the primary subscript refers to the dependent variables and the secondary subscript refers to the independent variables. Also, the ordering of the second subscript is immaterial. Thus, for example, R I.jk is equal to R I.kj, I is not equal to j, is not equal to k, equal to 1, 2, 3. Each of which represents the multiple correlation coefficient between the dependent variables xi and the joint effect of the independent variables xj and xk on xi. The square of the multiple correlation coefficient is known as coefficient of multiple determination. In particular, the coefficient of multiple determination corresponding to multiple correlation coefficient R1.23 is denoted by R square 1.23 may be interpreted as the proportion of total variation in the dependent variable that is explained by or is associated with the plane of regression of x1 on x2 and x3. The value of R square 1.23 may also be interpreted as a measure of the closeness of fit of the plane of regression to the actual data values. The values of R square 1.23 nearer to 1 indicate that the given data values are closely scattered about the plane of regression and hence it is a better fit. The value of coefficient of multiple correlation lies between 0 and 1, with a higher value indicating a better predictability of the dependent variable from the independent variable. Its value 1 indicates that the predictions are exactly correct, and a value of 0 indicates that no linear combination of the independent variables is a better predictor than is the fixed mean of the dependent variable. In other words, the closer R is to 1, the stronger the linear association, and if R equals 0, then there is no linear association between the dependent variable and the independent variables. The sample multiple correlation coefficient R measures the strength of the association between the independent explanatory variables and one dependent prediction variable. R can be any value from 0 to plus 1. Unlike the simple correlation coefficient R, which tells both the strength and direction of the association, R tells only the strength of the association. Capital R is never a negative value. Multiple correlation coefficient is always non-negative and lies between 0 and 1. Formula for two independent variables x1 and x2 is given by R is equal to square root of R square yx1 plus R square yx2 minus 2R yx1 into R yx2 R x1 x2 whole upon the square root of R1 minus R square x1 x2, where R yx1, R yx2 and R x1 x2 are correlation coefficients between the two variables, and R is the multiple correlation coefficient between the dependent variable y and the independent variables x1 and x2. Let us now look at the limitations of the partial and multiple correlations. This concept has certain limitations which are stated as: first, The computation of partial correlation coefficient is based on the simple correlation coefficient and it assumes linear relationship. This assumption is not valid in social sciences as it rarely exists in such phenomenon. Second, as we increase the order of partial correlation coefficient, the reliability of the coefficient decreases. Third, the limitations in case of multiple correlation are quite similar to those of partial correlation. If the multiple and partial correlations are studied together, a very useful analysis of the relationship between the different variables is possible. And last limitation is that another technique which can be used to overcome the limitations of simple correlation is multiple regression analysis. The partial correlation formula is as follows. R yx1 x2 is equal to R yx1 minus R yx2 into R x1 x2 upon square root of 1 minus R square yx1 into under the root 1 minus R square x1 x2. Multiple correlation studies the effect of all the independent variables simultaneously on the dependent variable. The value of the coefficient of multiple correlation lies between 0 and 1 and it is always a non-negative value. Multiple correlation formula for two independent variables x1 and x2 is as follows. R is equal to square root of R square yx1 plus R square yx2 minus 2R yx1 multiplied by R yx2 multiplied by R x1 x2 whole upon square root of 1 minus R square x1 x2. R represents the multiple correlation coefficient between the dependent variable y and the independent variables x1 and x2, and R yx1, R yx2 and R x1 x2 are correlation coefficients between the two variables. Simple correlation coefficient R tells us both about the strength and direction of the association, whereas multiple correlation coefficient R measures only the strength of the association. The computation of partial correlation coefficient is based on the simple correlation coefficient and it assumes linear relationship. This assumption is not valid in social sciences as it rarely exists in such phenomenon. As we increase the order of partial correlation coefficient, the reliability of the coefficient decreases. Thus, both the techniques suffer from certain limitations whose solutions arises in the concept of multiple regression.